One of the most important chemical properties of S-block elements, especially the group 1 alkali metals, is their extremely high reactivity. Reactivity refers to the tendency of an element to participate in chemical reactions by gaining, losing, or sharing electrons. Since metals generally react by losing electrons, the reactivity of a metal depends on how easily it can lose its outermost electron. Group 1 elements are among the most reactive metals in the entire periodic table, because each atom contains only one valence electron in its outermost shell. This single electron is weakly held by the nucleus and can be removed very easily during chemical reactions. The reason behind the high reactivity of alkali metals is their general electronic configuration, NS. Every group 1 atom has only one electron in its outermost s orbital. Atoms naturally try to achieve a stable electronic configuration similar to the nearest noble gas. The easiest way for a group 1 atom to become stable is by losing its single valence electron. After losing this electron, the next inner shell becomes the outermost shell, which already has a complete and stable electron arrangement. Therefore, alkali metals readily lose one electron to form positive ions carrying a +1 charge, represented as M. For example, lithium loses one electron to form Li. Sodium forms Na. Potassium forms K, rubidium forms Arb, and cesium forms Cs. Since only one electron needs to be removed, very little energy is required. This is why group 1 metals react rapidly with water, oxygen, halogens, acids, and many other substances. The image explains why reactivity increases down group 1. The first reason is that atomic size increases as we move downward. Every successive element contains one additional electron shell. Lithium has 2 electron shells, sodium has 3, potassium has 4, rubidium has 5, cesium has 6, and francium has 7. As more shells are added, the outermost electron moves farther and farther away from the nucleus. The greater distance between the nucleus and the valence electron reduces the attractive force exerted by the nucleus. According to Coulomb's law, the force of attraction between two charged particles decreases as the distance between them increases. Therefore, when the outermost electron is farther from the nucleus cannot hold it as strongly. The image highlights this point by stating that the valence electron moves farther from the nucleus as we move down the group. Since the electron is farther away, it experiences a weaker attractive force and becomes easier to remove. Another important factor is the shielding effect. Between the nucleus and the outermost electron are several inner electron shells. These inner electrons partially block or shield the positive charge of the nucleus. As more electron shells are added down the group, the shielding effect becomes stronger. The outermost electron therefore experiences an even weaker effective nuclear attraction. The image summarizes this by stating that nuclear attraction becomes weaker. The weakening of nuclear attraction means that the outermost electron is no longer held tightly. Consequently, the atom can lose this electron more easily during a chemical reaction. Because the outermost electron is both farther from the nucleus and more strongly shielded by inner electrons, it requires less energy to remove it. This energy is called the first ionization energy. The first ionization energy decreases steadily as we move down group 1. Lower ionization energy means that the atom can lose its electron more readily, which directly increases chemical reactivity. The image also explains this process using a simple sequence. Larger atomic radius, weaker attraction for valence electron, easier electron loss, higher reactivity. This flow summarizes the entire concept. As atomic size increases, the attractive force between the nucleus and the valence electron decreases. Because the electron is held less tightly, it is removed more easily. Easier electron removal leads directly to greater chemical reactivity. The image shows the reactivity trend of the alkali metals. Lithium, sodium, potassiums, rubidium, Cesium. This means that lithium is the least reactive. while cesium is the most reactive among the stable alkali metals. Every step downward in the group increases the ease with which the outermost electron can be removed. The vertical illustration in the center of the image demonstrates this trend visually. Lithium shows only a mild reaction. Sodium reacts more vigorously. Potassium reacts with greater intensity and produces a characteristic lilac-colored flame. Rubidium reacts even more violently, and cesium reacts explosively. The increasing intensity of these reactions reflects the increasing ease with which the outermost electron is lost. The increasing reactivity can be observed clearly when these metals react with water. Lithium reacts relatively slowly, floating on the surface while producing bubbles of hydrogen gas. Sodium reacts more rapidly, moving quickly across the water surface and often melting into a small silver ball because of the heat produced. Potassium reacts even more vigorously and usually ignites the released hydrogen gas, producing a purple or lilac flame. Rubidium reacts violently, while cesium reacts explosively with water due to the enormous amount of heat released. The general chemical reaction of an alkali metal with water can be written as 2M plus 2HO 2MOH plus H here. M represents any group 1 metal. During the reaction, the metal loses one electron and forms a metal hydroxide, while hydrogen gas is released. The reaction becomes increasingly vigorous from lithium to cesium because electron loss becomes progressively easier. Alkali metals also react readily with oxygen. Lithium mainly forms lithium oxide, sodium usually forms sodium peroxide, and potassium, rubidium, and cesium often form superoxides. The ease with which these reactions occur also increases down the group because of increasing reactivity. Similarly, alkali metals react rapidly with halogens such as chlorine, bromine, and iodine to form ionic salts. For example, 2Na plus Cl2NaCl in this reaction, sodium loses one electron while chlorine gains one electron. Because sodium can lose its valence electron so easily, the reaction occurs rapidly and releases a large amount of energy. Another important consequence of increasing reactivity is that alkali metals are never found in their free elemental state in nature. Since they react readily with oxygen, water, carbon dioxide, and many other substances, they are always found combined with other elements as compounds. Sodium occurs naturally as sodium chloride in rock salt and seawater, while potassium occurs in minerals such as sylvite and carnallite. Their high reactivity prevents them from remaining as pure metals under natural conditions. The image emphasizes that the outermost electron is farther from the nucleus and is removed more easily. This single statement summarizes the entire explanation of increasing reactivity. The outer electron experiences weaker nuclear attraction because of increased atomic size and stronger shielding. Consequently, less energy is required to remove it, resulting in higher chemical reactivity. It is important to compare this behavior with Group 2 elements. Group 2 metals have the general electronic configuration Ns and must lose 2 electrons to achieve a stable noble gas configuration. Removing 2 electrons requires more energy than removing only 1. Therefore, although Group 2 elements are also reactive metals, they are less reactive than Group 1 elements. Nevertheless, the reactivity of Group 2 also increases down the group because atomic size increases and ionization energy decreases. Another important trend is that although reactivity increases down Group 1, ionization energy decreases. These two trends are directly related. Lower ionization energy means electrons are removed more easily, and easier electron removal means higher reactivity. Therefore, ionization energy and reactivity vary in opposite directions. In summary, the high reactivity of Group 1 alkali metals is a direct consequence of their Ns electronic configuration, which gives each atom one loosely held valence electron. As we move down the group, atomic size increases, shielding becomes stronger, nuclear attraction becomes weaker, and the outermost electron moves farther from the nucleus. These changes reduce the first ionization energy, making the electron easier to remove. As a result, the reactivity increases in the order lithium to sodium dash potassium to rubidium and cesium. This increasing ease of electron loss explains why alkali metals react vigorously with water, oxygen, halogens, and many other substances, making them some of the most reactive metals in the periodic table. Understanding the relationship between atomic structure, ionization energy, and electron loss provides the complete explanation for the remarkable chemical reactivity of the S-block alkali metals. One of the most important trends in the periodic table is that the reactivity of Group 1 alkali metals increases as we move down the group. At first, this may seem surprising because the atoms become larger, but in reality, the increase in atomic size is exactly what makes these elements more reactive. Reactivity in metals refers to how easily an atom loses its outermost electron during a chemical reaction. Since every Group 1 element has only one valence electron with the general electronic configuration ends, the easier it is to remove this electron, the more reactive the metal becomes. To understand why this happens, we must first remember that atoms consist of a positively charged nucleus surrounded by negatively charged electrons arranged in different energy levels or shells. The positively charged nucleus attracts the negatively charged electrons through an electrostatic force. The strength of this attraction determines how tightly the electrons are held. If the attraction is strong, electrons are difficult to remove and the atom is less reactive. If the attraction is weak, electrons are removed easily and the atom becomes more reactive. The first step shown in the image explains that atomic size increases as we move down Group 1. Lithium has only 2 electron shells, sodium has 3, potassium has 4, rubidium has 5, and cesium has 6. Every new element has one additional energy level compared with the element above it. As a result, the outermost electron becomes progressively farther away from the nucleus. This increase in distance is extremely important. According to Coulomb's law, the force of attraction between two opposite electric charges decreases as the distance between them increases. Therefore, when the outermost electron is located farther from the nucleus, the attractive force exerted by the nucleus becomes weaker. The image illustrates this clearly by showing that the distance between the nucleus and the valence electron increases steadily from lithium to cesium. As the atomic radius increases, the outermost electron occupies a much larger orbit around the nucleus. Even though the nucleus also contains more protons, the greater distance prevents the nucleus from holding the outermost electron as strongly. Consequently, the valence electron becomes easier to remove. The second step shown in the image explains another important factor called the shielding effect. Between the nucleus and the outermost electron are several inner electron shells. These inner electrons repel the outermost electron and also partially block the positive charge of the nucleus. This means the outermost electron does not experience the full attractive force of the nucleus. As we move down Group 1, the number of inner electron shells increases. Lithium has only one inner shell between the nucleus and the valence electron, sodium has 2, potassium has 3, rubidium has 4, and cesium has 5. Because more inner electrons are present, the shielding effect becomes stronger with every step downward. The image explains that greater distance together with stronger shielding significantly reduces the attractive force exerted by the nucleus on the outermost electron. Although the nucleus contains more protons, the shielding produced by the inner electrons prevents most of this increased positive charge from reaching the outermost electron effectively. As a result, the effective nuclear attraction decreases. The image demonstrates this by showing that lithium has strong attraction, sodium has weaker attraction, and rubidium has the weakest attraction among the illustrated elements. This decreasing attraction is one of the main reasons why reactivity increases down the group. Since the nucleus holds the outermost electron less strongly, the electron can be removed more easily. The energy required to remove this electron is called the first ionization energy. One of the important periodic trends is that the first ionization energy decreases down group 1. Lower ionization energy means that less energy is needed to remove the valence electron. Because losing one electron is the first step in almost every chemical reaction involving alkali metals, a lower ionization energy directly leads to greater chemical reactivity. In other words, the easier it is to remove the electron, the faster and more vigorously the atom reacts. The image summarizes this relationship using a simple sequence. Larger atomic radius valence electron farther, from nucleus weaker nuclear attraction electron lost more easily higher reactivity. This flow diagram explains the entire trend in a logical order. Every step naturally leads to the next one, making it easy to understand why reactivity increases. The image also presents the reactivity order of the alkali metals: lithium, the sodium 9, potassium, Nance, rubidium 9, cesium. This means that lithium is the least reactive, while cesium is the most reactive among the stable group 1 elements. Every element below lithium reacts more vigorously because its outermost electron is easier to remove. The atomic diagrams shown in the center of the image reinforce this idea. Lithium has the smallest atom, so its valence electron remains relatively close to the nucleus. Sodium has one additional shell, placing its valence electron farther away. Potassium, rubidium, and cesium each have progressively larger atoms, causing the distance between the nucleus and the outermost electron to increase even more. The green arrows pointing outward represent the increasing ease with which the valence electron can escape from the atom. This increasing reactivity can easily be observed in laboratory experiments. When lithium is placed in water, it reacts slowly, producing bubbles of hydrogen gas while floating on the surface. Sodium reacts much more vigorously. The heat released during the reaction melts the metal into a small silver ball that moves rapidly across the water surface. Potassium reacts even more violently, and the hydrogen gas produced usually ignites, creating a characteristic lilac-colored flame. Rubidium reacts explosively, while cesium reacts so violently that it can produce a powerful explosion upon contact with water. The general reaction of an alkali metal with water is 2M plus 2HO 2MOH plus H. Here, M represents any group 1 metal. During the reaction, the metal loses its single valence electron to form a +1 ion, while water is converted into a metal hydroxide and hydrogen gas. Since the electron is removed more easily as we move down the group, the reactions become increasingly vigorous. The same trend is observed when alkali metals react with oxygen and halogens. Lithium reacts relatively slowly with oxygen to form lithium oxide, whereas sodium reacts more readily to form sodium peroxide. Potassium, rubidium, and cesium react even more vigorously, often forming superoxides because of their greater tendency to lose electrons. This increasing reactivity also explains why the heavier alkali metals require greater care during handling and storage. Lithium can be handled relatively safely under controlled laboratory conditions, but sodium must be stored under kerosene. Potassium requires even greater caution, and rubidium and cesium are so reactive that they are often stored in sealed containers under inert atmospheres. It is important to understand that reactivity is not increasing because the atoms contain more electrons. Instead, reactivity increases because the outermost electron is held less tightly. The increase in atomic size and shielding outweighs the increase in nuclear charge, making electron removal progressively easier. Another important point is that this trend is opposite to the behavior of nonmetals such as the halogens. Nonmetals react by gaining electrons, not losing them. Therefore, their reactivity decreases down the group because larger atoms attract incoming electrons less strongly. Metals and nonmetals therefore show opposite reactivity trends because they participate in chemical reactions differently. The same principle also explains why group 2 elements become more reactive down their group. Although alkaline earth metals must lose 2 electrons instead of 1, increasing atomic size and shielding still make electron removal easier as we move downward. However, group 2 metals remain less reactive than group 1, because removing 2 electrons always requires more energy than removing only 1. In summary, the reactivity of group 1 alkali metals increases down the group because atomic size increases, causing the outermost electron to move farther from the nucleus. At the same time, the shielding effect produced by additional inner electron shells becomes stronger, reducing the effective attraction between the nucleus and the valence electron. As a result, the first ionization energy decreases, the outermost electron is lost more easily, and the atom reacts more readily. Therefore, the order of increasing reactivity is lithium, sodium, potassium, rubidium, cesium. This trend demonstrates one of the most fundamental principles of chemistry. The easier an atom can lose its valence electron, the more reactive it becomes. Understanding the relationship between atomic size, shielding effect, nuclear attraction, ionization energy, and electron loss provides a complete explanation of why reactivity steadily increases as we move down group 1 of the periodic table.